All right. All right, medium today. Closest prime numbers in range. Given two integers left and right, find the two integers num1 and num2 such that left is smaller than or equal to num1, less than num2, smaller than or equal to right. So the numbers can't be equal, and they're in the num1 smaller than num2, and they're inclusively inside left and right. They're both prime numbers. Oh, okay. Num2 minus num1 is the minimum amongst all pairs satisfying the above conditions. The minimum amongst all pairs satisfying the above conditions. Okay. Return the positive integer array answer of num1, num2. If they're So the answer is the number. Okay, yeah. If there are multiple pairs satisfying these, return one with the smallest num1 value. If there's no such, if no such exists, return -1, -1. Okay. So the closest pair of primes within left and right and smallest. So what are the values here? Up to 10 to the 6th. Okay, so up to thousands, 10 to the third, so up to a million. Okay, so I think you have to. So do you have to start by identifying all the primes between left and right? Is that it? I think you do. Identify all the primes between left and right, and then just find the difference between them, consecutive differences. Do here. So if you iterate through all the values between left and right, like for a value in range left and right plus 1, then you do if is prime of value then prime is -1. If current prime is equal to -1, then current equals this value, else answer. I'm gonna say answer starts out. So you want to find the smallest one. Okay, let's go diff. Answer diff is going to start out with something large. Answer is going to be just an array. So value, the difference is the value minus the current prime. If this difference is smaller than the answer diff, the answer is equal to the current prime and this value. And the answer diff is equal to value, or it's equal to diff. I think that's fair. And then return guess answer should be originally -1, -1. Return the answer here. Now I just need to implement is prime. Is there a better way of going about this? This would, yeah, this is probably going to time out. Okay, this is, not sure what the quickest implementation of is prime. Fastest is prime diff Python. Okay, it's probably pretty fast. So let's see, what does this method do? If the value is 1, then it's not prime. If it's 3 or smaller, then it is prime. If it's divisible by 2, then it's not prime. Or if it's divisible by 3, it's not prime. Then everything in the range of anything bigger than that, so 5 and on, up to the square root of it plus 1, incrementing by 6. Incrementing by 6. I guess you took care of, how is this incrementing by 6? What's going on here? So starting with 5, if that number, oh no, these are divisors, okay. So you're looking at the divisors, starting with divisor of 5, and then moving on to divisor of 11. Huh, what is going on here? How does this method work? Base case is handled, divisible by 2 or 3 handled. Optimize iterations, iterates only through numbers of the form 6k plus 1 as all primes greater than 3 can be expressed in this form. 6k plus or minus 1. Really? I did not know that. I guess 5 and 7, 11 and 13, 17 and 19. Okay. So, wow. That's, how have I studied math so long and I've never realized that. Okay, well, I assume that that works well. Let's see how well this goes. Okay. Wrong answer. 19 to 31. I said 1923, and the answer is 29 to 31. I thought 29 to 31 would work. Why doesn't this work? Is prime, the current prime is -1, then you set that value. Oh, have I not actually, oh, whoopsie. Current prime equals value. Okay. Alright, so it works, but it's not optimized at all. Not even close. Okay, let's see this. Where's the description of this thing? Okay. How could I make this faster? My call is prime on, I guess I shouldn't really use evens. Like I could start with like odds. So I could do like the closest, I can go by twos here. And this would be starting with the first odd that's bigger than or equal to left. So I can do left is equal to left divided by 2 times 2. Same thing for left divided by 2. That's going to give me an even. I'll just do like if left mod 2 is equal to 0, then left plus equals 1, and if right mod 2 is equal to 0, then right minus equals 1. So if it's even number to at the bottom end, then it has to be becoming odd, bigger than it. Same thing for the, or similar for the top end. Okay. I mean, this thing doesn't probably change the speed all that much. I think it's probably too slow. If left mod 2 is equal to 0, so it's an even number, increase. And if it's right mod 2, that's an even number, then decrease it. Left. Okay, let's narrow the search here. Start left, right. Adjusted left, right. Wow, I may have used the wrong answer. Test case that. Alright, 1 to 999,000. Going by twos. Oh, it should start with 2, possibly. I see. Let's see. Where's the description? So I mean, if it has 2 within its range at all, then the answer should be 2, 3. So let's just do that base case. If left is less than or equal to 2, because left is smaller than right, right? It could be equal to each other. If left is less than or equal to, and well, and right is at most 3. Okay, I think that's narrows down that case. We're going to see how this goes. Slightly faster, but not fast enough. Okay, what else can you... So why is this slow? Is there a faster way to identify primes within a set bounds besides going through one by one? You test for something's prime, you go to the next one. Test for something's prime, you go to the next one. For I in the range 5. So you're testing these things that are possibly prime but not necessarily prime. And you're testing every single case, so you're testing like 5, 7, 11, 13 each time. What I guess you should be testing is the list of primes that we can compiled. So you can compile a list of primes up. So for instance, I mean, how good is this list? It'd be like 5, 7, 11, 13, 17, 19, 23, 25 is on that list. (31, 33, 37, 39). So some of this, no, 37, no, 35, 37. So you're testing for things that aren't necessarily going to work. Why is this a fast method? I guess you don't need to do as many loops in that case. Kind of combine in certain cases. People will use a lot of memory here. Okay. Optimization. I mean, I can store a list of primes that I encountered and just go through that list. And actually, if I see a pair that's exactly 2 away, I should be able to say stop. Right, so if the difference is equal to, if difference is equal to 2, then just return this answer. There's no way that it's going to get better than 2. Okay. Alright. Guess that was the key thing. Like a lot of primes, there's gonna be exactly kind of 2 away from the next prime, so if you see that, that's good enough. 1 optimization. Okay. Cool beans.